Some people, they do small introduction, what they do in their life, so maybe I should do the same. And I need to tell you that long time I kept lectures at the University of Warsaw, and after I changed my job, going to Polish Academy of Sciences. And of course, I did similar job because I am geologist and geochemist. And the topics I like very much. They are magmatic processes, magma generation, evolution, crystallization, geochemical modeling of magma evolution, and also the early Earth processes. And today the lecture will be about early Earth crust extraction. So let's start. Early Earth is loosely defined as Earth during first billion years of its development. And crust, what is crust? It is the outermost part of Earth, the outermost shell of Earth. And below we have the second shell called mantle. And if you look at the geological time scale, the early Earth, so first billion years of its development, it comprises the whole Hadean eon, starting 4.6 billion years ago, Eoarchean eon, starting 4 billion years ago, and partly Paleoarchean, starting 3.6 billion years ago. Hadean, I even will not ask you where from the name, because it is fully clear from Hades, Greek god of underworld and the underworld itself. The name was given because people imagined hellish condition on Earth at that time. So a very hot planet after recent accretion, with a lot of radioactive elements and with frequent collisions with bodies from solar system. And the first crust extracted during Hadean, we believe, and okay, we have also some proofs, is presumed to be of ultramafic and mafic composition. But small pockets of felsic material was also discovered. So to begin with, we need to define what ultramafic, mafic, and felsic rock is. Ultramafic and mafic rock is dense, dark, enriched in iron, magnesium, and calcium, and is relatively silica poor. And felsic rock, in turn, is silica-rich, along with aluminum and alkalis, and is of light color and less dense. And this is really important for us because, you know, looking at all these three items, we can make a chain using all of them. Namely, to crystallize mafic and ultramafic rock, we need melts from the mantle. From the ultramafic rock, a big degree of partial melting of the mantle, for mafic rock, smaller degree of partial melting of the mantle. And now, what is partial melting? If you assume a certain volume of a rock, and you want to melt the volume. After some time, when the process proceeds, you will have a fraction of melt and something what is not melted. And this not melted part we call a residuum. So now to have melt for ultramafic rock, we need to melt 50% of the volume. And for mafic rock, a smaller degree. But you know, mafic rock is also very important for us because if we melt mafic rock, we will have melt ready to crystallize silica-rich rock. So that was a very small introduction. And I need to tell you something, namely, In the lecture, I would be happy to show to you some research on the oldest rocks and minerals on Earth. But the lecture before was always prepared by Hervé Martin. And he was a very great, oh my God, that's emotions, very great personality and very, very great scientist. And he passed away last year. And that is why the lecture is in memorial. Sorry. Let's have a look at continental crust evolution. And first, please look at the upper part of the cartoon and after at the lower part of the cartoon. If you look at the upper part of the cartoon, there is a chain showing rocks names. And the chain starts with a greenstone belt. Greenstone belt is composed of lava flows of ultramafic and mafic composition. But immediately after, the next item is TTGs. And TTGs, tonalite, strontiumite, granodiorite, these are silica-rich rocks. And the next item, of course, again, silica-rich rock. Sanokitoid is granitoid and rich in magnesium. And why the silica-rich rocks are so important for us? Because they are able to stabilize the first terrains on Earth. So now please look at the lower part of the cartoon. We have the Hadean Eon. And there is no rocks name within Hadean Eon. And Martet told you we have no rocks from Hadean Eon. No one rock survived Hadean Eon. Okay, small pieces, yes, they survived. So mostly the material from Hadean Eon is limited to single minerals, to zircons. And zircons, they are very resistant to alteration, so that they can be transmitted from older rocks to younger rocks. That's the first reason zircons are so important for us. But the second reason is that zircons, they have a lot of trace elements included into their structure. And the trace elements, they are an excellent source of information about conditions of zircons formation and transformation. So we have no rocks, but we have minerals giving us a lot of pieces of information. And if you look after Hadean time, after Hadean Eon, we have Archean, and within Archean, TTGs. And there is a name, Akasta, mentioned also in her Mart lecture, a very important place, because some small pieces of the crust there are dated on late Hadean Eon. And next we have also TTGs together with Sanokitoids, Capval, Craton. So you know, TTGs stabilize the cratons, so they are crucial for us to understand the process of early crust extraction. But I need to tell you that if we would be able to answer a question why we have almost nothing from Hadean Eon and we have such a big jump in the crust volume during Archean Eon, we will be also able to speculate what was the process of crust extraction and destruction during Hadean Eon. And I hope we will answer the question today with use of some publications. So, you know, I told you that if TTGs are able to stabilize terrains, we should expect that quite a lot of rocks of this early Archean terrains will be preserved up to the present day. And indeed, if you look at the red patches, these are Archean terrains, and everything what underlined the Archean terrains is shown here in orange color. And some famous names, namely Akasta. Here are these small pieces of rocks dated on Hadean Eon. And the next one, I'll look at Greenland. 3 items. I will show to you some pictures from the rocks next. And the third place, Jack Hill's conglomerates, because here the oldest Hadean zircons have been found. And you know, a lot of research was done on Jack Hill's zircons. And I will try to present some of them for you, because the results and also the discussion on these results is very interesting. And the question is if Jack Hill's zircon is the only one of Hadean Eon. Now, here we have a map taken from Mulder et al. 2021, and all the spots on the map, they show other foundings. So we have quite a lot of Hadean zircons found all around the world. So quite a lot material for our research on early Earth extraction. Okay, some rocks. Isua greenstone belt, ultramafic lava flows of Eoarchean age with a very beautiful flow textures. And 2 pictures. One is Amitsoq gneisses, the second one Isua again, both from Greenland. And if you look at ages of these rocks, they are Eoarchean. So on the left we have gray rocks. They were emplaced as magmatic rocks, TTGs, so tonalite, trondhjemite, granodiorite. But of course, you know, almost 4 billion years of different processes cause that these rocks, they are metamorphosed, and now they are gneisses. So also silica-rich rocks, however, with different textures and structures. And the white dike cutting the gray field of the rocks, this is pegmatitic dike, and the pegmatitic dike is much younger, so it's not Eoarchean age. And if you look at the picture on the right, these are the oldest sedimentary rocks found on Earth. And again, the same situation during Eoarchean time. This was a sediment. However, during so long time, the sediments have been metamorphosed, and now we have gneisses. So we have now rocks from Hadean Eon. And we want to model crust extraction during Hadean Eon. How to do it? We have some models, and generally the models are constructed using some assumptions and data. And the most important here is knowing how much crust was added and removed throughout Earth's history. And to give you an image how difficult it is or how complicated it is, I want to show to you the present day geological settings where crust is added and removed. So please look at the numbers above, and they show the amount of crust added per year in cubic kilometers. And if you look at the numbers below, this is the amount of crust removed exactly at the same time. During 1 year and in cubic kilometers. And we have three different settings, convergent, collisional, and extensional. And now if you look at the environment where we have a very fast crust recycling, this is subduction, the plate is going down to the mantle, collapsing, being melted. And sometimes if the plate is old, it is rolling back a little bit, and we have here extensional environment, and a little bit crust is added at that place. But mostly the crust is added within accretionary erosion. Where else? We have mafic magma underplotting at marginal parts of the continents and also below the continents. And the melts, they are contributing to the crust formation. We have such an environment of hot spots, so heat pipes. The mantle is melted, the melt is going up and is contributing to the crust formation. But within collisional erosion, we have crust thickening, and we have additional melts within the crust. So also the melts are contributing to the crust formation. But sometimes, if the crust is really thick, we have delamination of the crust. Some parts that are going to the mantle being melted. And within extensional environments, we have mantle melting. The melts are going up, and also they are contributing to the crust formation. So we have a lot of places where crust is added, and some places where the crust is recycled, is consumed. But if you look at the numbers above and below, you may tell, but this is almost the same. So the sum of the numbers above and the sum of the numbers below, they are approximately the same. So it means that we do not observe net crust growth at the present day. But the question is, if the same factors controlled the crust extraction and recycling during early Earth history. Because we don't know much about it, and that is why models which are constructed, they are not entirely equivocal. Still, they are constructed, and I want to show to you some of them, and just look how different they are. These are continental crust growth, so the models they show cumulative volume of the continents extracted throughout the Earth's history, especially during early Earth history. And if you look at Armstrong's model, he was of the opinion that almost everything was extracted during Hadean time and at the very beginning of Hierarchian time. In turn, Goodwin model, almost nothing extracted during Hadean time and also Archean time. Everything is much younger, so maybe Proterozoic or even younger age. And somewhere in between, we have Bielosova et al. Model. And the model predicts that at the very end of Archean time, more or less 60 to 70% of the crust volume was extracted. But they also ask a very important question, telling actually we don't know how much Archean crust was consumed throughout the Earth's history. We don't know how much Archean crust is hidden within middle or lower Earth's crust. We don't know how much Archean crust was extracted using ancient reservoirs, or how much crust was extracted using juvenile melts. And there's two possibilities I will explain in detail using the last model today. So what was the assumption used to speculate about the crust volume extracted? The first one is we used zircons. That we call zircons because I told you that zircons, they may provide us a lot of pieces of information about the early period of crust extraction. The second method was to use isotopic systems, especially looking for ultramafic, mafic crust extracted, and in turn felsic crust extracted, because I told you all these three items are interconnected. Yes, so ultramafic, mafic directly from the mantle, but if we will melt mafic crust, we will have felsic crust. And you know, the system, the isotopic system, is extremely sensitive, what also Mart showed to you before. So looking for isotopes, especially we will concentrate today on lutetium-hafnium system. We may tell what was the dynamic of the crust extraction throughout the ages, and what was the magma source for the crust. And you know, we also use the isotopic systems to speculate about the mantle composition throughout the Earth's history, because if you extract melts from the mantle, you change the composition of the mantle. We call this mantle depletion. So measuring the mantle signature, we also may tell something about how much crust was extracted from the mantle. The third method is to use a direct estimation of the volumes of the rocks that are formed throughout the Earth's history. And in the lecture today, we will concentrate on the first and second possibility, so maybe the third one next time. Zircons. I told you, extremely important mineral, however, of a very simply formula. Just look to crystallize zircon. We need only few elements: zirconium, silicium, oxygen. That's all. And also the structure of zircon is not very much complicated, because if you look at the axis here, this is C-axis, we have two basic elements, namely silicium oxygen tetrahedra, sharing edges and corners with zirconium oxygen dodecahedra. And along this axis we have alternating tetrahedra, dodecahedra, tetrahedra, dodecahedra. And if you look along the perpendicular axis, we have only zirconium oxygen dodecahedra, and they will form zigzag chains. And looking inside the structure, we have additionally two items, namely zirconium elongated and shortened tetrahedra. Are these items so important for us? To some extent, yes. But you know, what is really important is that they form a lot of channels and voids. And within the channels and voids, we have a lot of trace elements. And you know, two are most important: uranium lead. Why this is so important? That was the previous lecture, because uranium decay to lead give us the possibility to date the crystals and directly also the rocks. But we have also a hafnium lutetium system, isotopic system, and I told you we may, with use of this isotope, speculate about the crust extraction. And together with dating, we may tell when the extraction took place. And we may also answer a question, where was the magma from? So crustal origin or mantle origin. And we have also titanium. And if zircon crystallizes in equilibrium with some other minerals like rutile, this is titanium oxide, and quartz, we may use titanium to speculate about the crystallization temperature of the mineral. So we have the thermal conditions of the crystallization. And what else? For instance, rare earth elements, because they give us information about magma evolution. So they are really very, very important. And what else? Oxygen isotopes, because they give us information also about magma source. And also some mineral inclusions. If you look here, every one inclusion is also a source of information. So we have a lot of possibilities to extract many pieces of information. And that is why zircon is so good source of information for us to do very sophisticated research on the crystals. And in addition, if you look at this column here, these are cathodoluminescence pictures of zircons. And if you look at them, the zircon's development is very complicated, a lot of zones. So we may, for instance, date every one zone, and together with other pieces of information, so trace elements composition, we may tell what environment it was within which zircon crystallized, magmatic, metamorphic, hydrothermal. So the zones are sometimes very regular, sometimes not. They show some processes of dissolution, recrystallization, and we may tell zircon is like an archive of the Earth's history. Is something what we may call that it registers all hallmarks of the Earth's history events. Okay, if this is right or not, please look also at the data here. Some zones, they have been dated. The numbers are different, what means that the timing of the whole crystal formation or recrystallization was quite long, and we may precisely tell what zone at what time was formed. So I told you zircons and isotopes, and also within zircons, isotope systems are very important for us. And here I want to show you just one sentence from Peterson et al. Publication, and because it is a very good summary, they told due to the minuscule amount of preserved Hadean to Paleoarchean rocks, models for the generation and evolution of continental crust during the first billion years of Earth history emphasize long-lived radiogenic isotope systems, and we will use lutetium, hafnium today. Okay, what geochemical parameters we use to show the crust extraction? It was also shown by Mott for samarium. Yes, epsilon. Here we will use epsilon hafnium. So we need values of epsilon hafnium 176, 777, and the ratio is in our standard, and the standard is the dendritic uniform reservoir. So the composition of undifferentiated meteorite. We may calculate the same ratio for our samples, and then the ratio estimated in our samples and related to the standard will be our epsilon hafnium. And if you look at the cartoon, the line epsilon hafnium 0 symbolizes the very beginning of the whole process of the crust extraction. At the same time, we believe that this is the value of bulk silicate earth. And now looking at these arrows, if we will have the crust extraction process, epsilon hafnium will go towards less radioactive values, so negative values, and if we will extract a lot of material from the mantle, epsilon hafnium will go towards positive values. And I want to draw your attention to Jekyll's points, the outcomes of the research on Jekyll's zircons. And you know, the cloud is not very well defined. So some of the points, they are close to epsilon hafnium 0, and we may maybe interpret it that the parental melts for the rock in which zircon crystallized, whatever the rock composition was, so probably silica rich, was derived from the mantle, so the original melt. But you know, the cloud here, it shows that the residence time of the Jekyll's crystals was quite long. Why I tell quite long? Because if you look at the very beginning of the crust extraction, this is about 4.4 billion years ago. But during the first 300 million years, we may tell, okay, more or less the composition of the crust was not very much changed, so it was intact. And this is also a problem. You know why? We have a lot of data derived from research on Jekyll's crystals, but the interpretation of the data is totally different. Namely, the discourse about the data is very lively, and the scenario, they range from hot, dry Hadean eon up to full-blown plate tectonics environment with oceans and fully differentiated crust during Hadean eon. So fully differentiated crust means able to stabilize the terrain, so silica rich. And now I will show to you some investigations showing these different interpretations. On the right, we have cathodoluminescence picture of Jekyll's zircon. A small part is dated for 4.4 billion years. And we have also very small pocket of ferric material here. And the publication was done by Harrison et al. 2005. And they measured hafnium isotopes within Jack Hill's zircons, and they got two different populations. One with positive values and the second one with negative values. So if you remember the last cartoon, you may interpret it immediately telling, okay, negative values, they will point to crust extraction. And together with dating, we may tell, okay, the crust extraction occurred as early as 4.4 or 4.5 billion years ago. But the positive values we may interpret in such a way that we need a very big change in the mantle composition. What means that we need to recycle our crust into the mantle. And if you remember the present day geological settings, the settings where we have very intensive crust recycling is subduction. So Harrison et al., they draw conclusions that as early as 4.4 billion years ago or 4.5 billion years ago, we also have subduction, so during Hadean time. And you know, immediately after, another paper was published, also Jack Hill's zircons. And if you look at the pictures on which the research was done, they have very complicated textures with a lot of zones, and some of them we may interpret as magmatic zoning. However, this here is something like a very complicated origin with dissolution and reprecipitation or recrystallization. And some parts of these crystals were also dated, and the numbers are, okay, different. Long timing of the crystals formation and transformation. And Valley et al., they stated none of the data cited by Harrison, and including interpretation that the crust was very much evolved, so silica rich, and that we had subduction during that time, that none of the data uniquely support the hypothesis of plate tectonics and subduction as early as 4.4, 4.5 billion years ago, or complete differentiation, so formation of silica-rich crust during Hadean time. And they also point to the difficulty in interpretation because they tell, if you look at zircons textures, they are very complicated. And every one zone may give you a different piece of information. So we need a lot of investigation on zircons on every one part of the crystal to have a good piece of information about the environment in which the crystals were formed or transformed. And they state that such studies are in their infancy, and we need to do a lot to have strong arguments. But you know, almost recently another paper appeared, and the idea about plate tectonics was coming again. Namely, the paper Turner et al. 2020, they measured trace elements composition of Jack Hill's zircons, and after they recalculate the trace element composition of the crystals into melt composition, also in ppms. If you look at the cartoons here on the right side, they used thorium, ytterbium, niobium, dysprosium, and many, many others. And how to do the recalculation? We need to have partition coefficient. And partition coefficient is a ratio between a trace element composition of the mineral, so trace element concentration in a mineral, to a trace element concentration in a melt. So if we have partition coefficient and we have trace element composition in the mineral, we may recalculate these values into trace element composition of the melt, what they have done. And here is the result of the recalculation. And in the bottom, I showed to you the cartoon I already showed you before, because there are some present-day geological settings. And if you look at the recalculation, these are the black points. First, looking for the Harrison et al. Conclusion. This is evolved crust. If this is evolved crust, it must be silica rich. So maybe TTGs. But our points from recalculation, they do not fit to the TTGs field. Okay, first disappointment. But after, if you look at another piece of information, that melts extracted during early Earth development, they were of ultramafic composition, so from the mantle. We should expect that they should come from, for instance, this heat pipe or mob, yes, so extensional environment. And this is not the case. The blue field, no points from recalculation. The red field also no points from the recalculation. So where are the points? The points are within model arc lavas, so subduction. And if you look at the lower part of the cartoon, here is an axis, subduction, and our points, they gathered along the axis. So their conclusion was maybe really very early in the Earth's history, we might expect plate tectonics and subduction environment. And in addition, if you look at the left part of the cartoon, here we have a temperature calculation for the rocks, and the temperature is quite low, like for very evolved crust, granitic rocks, and very low temperature. And if you look at the silica content recalculated, okay, it starts from intermediate composition, like andesitic composition, but it is going up to really evolved crust. So now this is the difficulty in the data interpretation, that we have some data and people draw totally different conclusions. Okay, they are all very interesting because they open next and next chapter in the interpretation of the data. But once we have an interpretation, for instance, we have plate tectonics very early. The second one, no, we have no plate tectonics. Once we have evolved crust, and the other interpretation, no, we have no evolved crust. Once we have high temperature, so hot planet, and other interpretation, no, the planet was not so hot and maybe a little bit wet. If the temperature is so low as Sterner et al. Interpreted, 700 grades Celsius, maybe we should look at the felsic pockets within Jack Hill's zircons. And here I need to tell you that a very good geochemical factor to interpret if the magma is evolved or not, and what was the magma source for the pocket, we need to use oxygen isotopes. And we use delta oxygen 18. Here is an explanation how to calculate the delta, of course, in relation to standard. And the value is expressed in promils. And for some environments, we have some estimated values. For instance, for the mantle, the average value is 5.5 promille. For the crust, the value is higher. And here, of course, the oxygen values were also measured for Jekyll's crystals. And the values were a little bit elevated. So the interpretation was maybe Hadean time was not so hot, maybe a little bit wet, and maybe some crustal addition to the parental magma. And here I want to tell you about another publication by Nemchin et al. 2006. And they stated that if we will filter the oxygen data and using very strict criteria, we will have no evidence of a little bit lower temperature on Earth during Hadean time. And also not evidence that Hadean time was a little bit wet. But you know, the oxygen research is really interesting because, and this is the last paper I want to show to you. From the collection, we have data, but the interpretation is so interesting because it is different. The last paper is about olivine. Olivine is magnesium iron silicate, and it crystallizes as a first mineral in ultramafic mafic rocks. But it is very sensitive to alteration process, so it is very difficult to find fresh olivine if the rock is very old. And just look, these are olivines within very old ultramafic rock, Komatia, and the volcanic rocks, the komatitic rocks, are 3.3 billion years old. And the olivines, they are not transformed, they are not altered. So an excellent material for research, and they use the olivines to measure oxygen values within olivines. And here you a very big surprise, namely I told you that the average value for the mantle and komatitic rocks, they are coming from the mantle. No doubts, only mantle melting may give us komatitic melts, so ultramafic melts. The value for oxygen is very, very low. So delta is between 3 and 4, and it doesn't keep the average value of the mantle. So why so low? And there is a lot of explanation why is it so low, but I want to tell you just one because it is related to Hadean time, even if 3.3 billion years means that this is Paleoarchean at the time. 2016, two papers appeared by Sobolev and Herzberg. And their idea about Hadean mantle was that during Hadean eon, the mantle underwent a very strong ingassing. A lot of volatiles was introduced into the mantle, and with the volatiles we also may expect very big oxygen heterogeneities. And if the mantle was homogenized, this heterogeneity disappeared, and we have the 5.5 value for the mantle up to the present day. Okay, so note this part that was some single papers with some populations of data and interpretations ranging from the different scenarios, but I think they are interesting because, you know, science is predictable and unpredictable at the same time, and if we have something new and we want to interpret it in a very interesting way, we try to find something really exciting, and I tried to use such papers where you can be convinced that the interpretations was really totally different. So now we will switch to some models. Models of crust extraction, and we will use data from Pilbara, the terrain, a very well preserved terrain of Archean age. This is Western Australia. Also a lot of investigations have been done on Pilbara rocks. The first model I want to present to you is by Patterson et al. 2020. They used rocks from Pilbara craton, and here are the names of the rocks. So they are TTGs, they are gneisses, and so on and so on. But from the rocks, they separated zircons, and first they measured oxygen isotopes signature. And if you look at the values, their opinion was, okay, more or less the value keep mantle-like signature. So the conclusion was parental magma was derived from the mantle. Maybe the rocks are not the direct product of the mantle-like magma crystallization, because I told you that to have silica-rich rock, we need to melt mafic rock. So first to melt mantle, after to crystallize mafic rock, after melt mafic rock, and then we have melt for felsic rocks. But still, their opinion was the rocks, whatever was the path of their formation, the rocks kept mantle-like signature. So the mantle was not depleted. And the same conclusion they draw using epsilon hafnium value for the same rocks here, exactly for the rocks. And if you look at the data, they keep more or less the line epsilon hafnium 0. Maybe not so much, however, the conclusion was more or less, yes, it is epsilon hafnium 0. And they wrote something like that, okay, some previously published data, they do not fit to the line, and some they fit perfectly well, like Kemp et al. The data. Exactly the line, epsilon hafnium 0. And please look at the rocks, they are of Eoarchean age to Paleoarchean age. Nothing from Hadean age. From Hadean age, we have nothing. And you know, their conclusion was the parental melt was from not depleted mantle. Why? Because the depleted mantle line is here, the dashed line, and the data, they do not fit to the dashed line. And I want to show to you the conclusion, their conclusion. Namely, the common assumption of a linear evolution of a depleted mantle from 4.5 billion years to the present day is inappropriate. For determining the timing and the volume of continental crust extraction in the Archean. The nearly identical early evolution of the Pilbara and Capval terranes suggests a common process to generate Archean granite greenstone terranes that does not require extensive reworking of the ancient crust, but rather involves juvenile crust addition above persistent zones of upwelling hundreding mantles. So now, if there is no crust recycling, no plate tectonics. Everything is extracted from the mantle. And now I want to show to you the model, because the model is really very interesting. Just note, this is Archean time, and the model starts with an age 3.6 billion years ago. So we may expect that the crust at the time was already quite thick, extensional environment within the crust, ancient continental nucleus at the very bottom of the crust. The crust is volcanic plateau, and it is above upwelling mantle. And upwelling mantle is an excellent environment to melt the mantle. So now what we may expect next is intensive mantle melting. And the melts, they are going up. And if you melt the mantle, you may expect mafic or ultramafic melts. So we may have first magmatic bodies of mafic composition, and if we will melt the mafic composition, these bodies, we will have first TTGs within the crust. But you know, at the same time, if you melt a mantle, I told you that not everything is melted, that we have residuum after melting. And the residuum is very heavy because it is composed of pyroxene and garnet. And because it is heavy, it is going down to the mantle. And the process of the residuum diving into the mantle is causing catastrophic fast of the mantle melting. A lot of melts is extracted and is going to the surface, all of them ultramafic composition. And of course, everything else is also proceeding, namely TTGs formation, mafic bodies formation, and a lot of residuum is appearing within mantle, even a signature of depleted mantle. Now, within this period, we also have first intracrustal melting. It means we melt TTGs. And you know, every one next melting causes more silica-rich melt. So we have granitic melts. The melts are also transmitted to the surface, and they form something like the domes. Okay, now the configuration is very peculiar. You know why? Because the ultramafic melt is very dense, it's very heavy, and the silica-rich melt is light. So we have instability between ultramafic melt and silica-rich melt, what is leading to gravitational overturn. Now, this is a rule by Rayleigh-Taylor rule. And what happens? The heavy melt, ultramafic melt, is going down, forming keels. And the light melts, granitic melts, they are welling up, forming domes. And the final product, which we observe, just look, this is Paleo-Archean at the time. The final product is well visible on satellite picture done for Pilbara terrane. You have the yellow spots, and these are granitic domes. And in between, we have a lot of ultramafic mafic curtains, so keels. They are fully deformed, and they separate the light granitic domes. So, okay, the model is for me excellent because in the nature we have some proofs it works. And now I want to show to you another one. It is very similar to the last one, but you know what is so exciting here, and what additional piece of information we have looking at the model. Wimmer et al. Model 2018, they stated to have fully stable craton, full stable continent, full stable crust, which is able to enter plate tectonics environment, so it's rigid enough to enter plate tectonics environment. We need 3 times of gravitational instability. And please look at the cartoons. We will only look at this part because it is most important for us. Everything what is the orange, red, or even gray is intracrustal melting, silica-rich melt, and everything what is green, gray, green is mafic, ultramafic melt. So from the mantle. And you know, if you look at the first picture, we have a very thick protocrust, more than 40 kilometers thick. And at the very big depth, over 40 kilometers, we have the first intracrustal melting. So we have silica-rich melts here. And of course, we have also residuum after melting. It is going down to the mantle. But you know, the melting is not just one event. We have next and next events. And you know, due to next and next impulses, the silica-rich melt is forming something like a bubble structure. And the bubbles, they want to well up because they are light. And everything what is of mafic, ultramafic composition tends to go down because it is heavy. So we have the first instability, gravitational overturn. Our bubble is going up to the surface. And mafic, ultramafic melt is going down. But you know, the process is not finished because the next period of mafic, ultramafic melt extraction from the mantle will cover our bubble, but the bubble does not give up. It wants to well up again. Yes, because this is light melt. So it is going up, the second gravitational overturn, and during the third one, we have the stable configuration. Namely, we have granitic domes, and we have this ultramafic mafic curtains fully deformed and separating the granitic domes. So exactly what you saw on the planetary image from Pilbara crater. Okay, so one more model. But I promise you, this will be the last model for Yilgarn crater. And to make a short break, some funny pictures because you know Yilgarn crater is also interesting for Salton, not because of the model of early crust formation, but because of gold prices on the stock exchange, Iligan Craton has also gold deposits. And what is the model? And why is so interesting for me? Because, you know, up to now, I told you, okay, we have a lot of data for Archean rocks. We have some data for Hadean zircons, but we have no Hadean crust preserved up to the present day. But the model explains that the Hadean crust, it didn't disappear without any traces. It was simply transformed to another form. And that is why it is so valuable for us. So we need to cancel such a knowledge. We have no Hadean crust. Yes, we have. However, we need to look how to discover what traces are from Hadean eon. And please look at the cartoon, again, epsilon hafnium systematics. And here we have some dark blue spots, zircons from evolved rocks from Hadean time, because I told you that some pockets of evolved crust were also present during Hadean time. And these zircon data, they define a field of Hadean crust, and through interpolation, the field is going to the left part of the cartoon. But the left part is extremely important and interesting for us. And just look, within the left part, we have something like vertical trends, which are anchored to the line epsilon hafnium 0. And if you look at the first trend, because it is consistent, well developed, we may tell, okay, there are two different parts. The first one is here, and the second one is here. So now we need to go back to TTGs, because these are evolved rocks stabilizing cratons, and the data are for evolved rocks. To have TTGs, we need to melt mantle, to have mafic melt, crystallize the mafic melt to a mafic crust, to melt the mafic crust, and ready. We have melt for TTGs. And if zircons will crystallize within TTGs, we will have pieces of information about the environment. So if you look at the first population of data, you may tell, okay, this path is a very short path. Namely, we have mafic, we have mantle melting. The melt is extracted, and almost immediately after, when the mafic crust is crystallized, the mafic crust is melted or remelted, and we have melt for TTGs. And you know, if the path is so short and the processes, they are going one after another, the zircons in TTGs, they will keep epsilon hafnium more or less 0. So they will preserve the original mantle signature. But there is another possibility. We have ancient Hadean crust, very old. And we also, the Hadean crust may also be mafic. And we may melt the Hadean crust, mafic crust. So we will have the same melt ready to crystallize TTGs. But if within the TTGs zircons will crystallize, the signature epsilon hafnium of these zircons will be negative. So we have two parts, two different processes, and you know, due to the knowledge, which one signature we may relate to which one process and which one environment, we may differentiate between TTGs derived from ancient Hadean crust and TTGs derived from fresh melted mantle. And that is why I told you, no, Hadean crust did not disappear. Hadean crust is somewhere hidden, the information is somewhere hidden, but we may extract the information doing precise, describing precisely the process of TTG's formation, so the crust which stabilize first continents. So let's have a look at the block diagrams provided by Mulder et al. This is Hadean lithosphere, and below is Hadean hafnium isotope systematics, and Archean lithosphere with Archean hafnium isotope systematics. These bars, they show crust evolution and mantle evolution. And if you look at the first block diagram, we have convecting mantle, and we have a stratified lithosphere with ultramafic crust here. And due to the impacts or due to a small intercrustal differentiation, we may have small pockets of felsic material. And if we have zircons from these small pockets, the zircon epsilon hafnium will keep the value within this area. Okay, now we jump from Hadean to Archean at the time. And you know, we have some really very interesting environments. The first one is subduction. The Hadean crust is recycled here, it's consumed. And we have also a lot of mafic melt extracted within this area. This is juvenile males. And if we will form fresh mafic crust, and after we melt the crust, we will have melts for TTGs, and these dark yellow spots, these are TTGs formed in such a way. So, juvenile male from the mantle, fresh mafic mantle, fresh mafic crust, remelting, and TTGs from the melt. But you know, we also have here the light spots. And the light spots, they are also TTGs, but they are from direct ancient reservoir melting, so Hadean crust. And this is better visible here within this area, namely, we have upwelling mantle. A lot of mafic melt is extracted from the mantle, what also causes that the mantle here is thick, buoyant, and also depleted. And we have here a freshly formed mafic crust. If we will melt the crust, we will have juvenile TTGs with the signature within this area. But if we will melt directly Hadean crust, having TTGs, these light yellow spots, the zircons signatures within these TTGs will be within this area, because we melt old crust, ancient crust with a long residence time. And you know that this is the whole mystery why we do not observe Hadean crust, but we still may extract information where the crust is preserved in what TTGs, what part of the TTGs formation can give us information about ancient Hadean crust. And you know, the picture here is very interesting, because if you look especially at the pot, we have the first plateau stabilizing the first terrains. But in addition, we have also a thick buoyant melt depleted mantle, which in addition stabilize the whole system. And that is why this system was able to survive up to the present day, and that is why we have so many terrains of Archean age. Okay, that was enough about models. Probably I killed you with models. I want to tell you there was a lot told about zircons, but we also use other accessory minerals, and two of them are important, namely titanite, calcium titanium silicate, and apatite, calcium phosphate. And if you look at the diagrams, the triangular diagrams, they are constructed with use of trace elements, light rare earth elements, strontium, yttrium. You may recognize, and for apatite and for titanite, you may recognize some field with the names which are well known for you, TTGs or sanokitoids. So with use of titanite and apatite, we may differentiate between these Archean rocks. And the same, we may use normalized diagrams, rare earth elements. The normalization is to chondrite, but the normalization can be to other sources, for instance, to primitive mantle. And with use of apatite and titanite, we also may differentiate between some rocks types. And here at the bottom, I showed to you a very small diagram. I promise I will be not emotional now. The diagram was introduced by Moya and Martin, 2012. It is used up to the present day, and it allows us to differentiate between TTGs and modern granitoids. So now, at the very end, to make the atmosphere more lighter, like silica-rich melt and melt which stabilize cratons, I want to tell you a small anecdote. Namely, I work a little bit with Hervé Martin. I invited him to Warsaw to give some lectures on early Earth development, or magma evolution, or modeling of magma evolution. And during talks, he asked me about my opinion about the most interesting magmatic rocks in Poland. So I told him, of course, composite Pluton, because it has two magmas from the mantle and from the crust. And he asked me, and the age? And very proud, I told him 320 million years. So the answer was too young for me. Okay, so you know, we still made a nice model for the batholith origin, and we publish it. And next, Hervé supposed to me research on another batholith in India. Indian colleagues will be happy now. Closepet, Darwa Craton, 2.5 billion years old. And we did research on the late Archean hydrothermal system. Here are some titanites which are changed due to fluid mineral interaction. And you know, looking for explanation too old, too young, I can tell you 2.5 billion years is not enough for the present lecture. Because during the present lecture, we were interested in 4 billion years old minerals, rocks. So actually, everything in geology is very relative. Too young for us, too old for us, not young enough, not old enough. And I need to tell you that looking at the geological time scale, we are all very young and forever young. And with this simply statement, I want to finish my lecture. Thank you for your attention. What is in Polish? Dziękuję za uwagę.